Hey, today we're going to talk about forces on current carrying wires, a natural progression from our discussions about charged particles moving through magnetic fields. So let's first of all remind ourselves about what we know about wires carrying current. And the biggest thing is this one right here. A wire with a current through it has a magnetic field. Now that's important because whenever you have something with a magnetic field, then you have the opportunity to influence it with another magnetic field. And that's what's going to happen here. So when placed in an external magnetic field, so it's got its own magnetic field that it gets created when a current flows through it. Now we're going to put it in another magnetic field. And when that happens, it may, this is important, it may have a force on it. Just like charge moving through a magnetic, sorry, yeah, this should be magnetic, moving through a magnetic field may have a force on it if the conditions are right. So let's take a look at a picture here to help us understand the relationship between those two phenomena. So if you consider an electron here, if this electron starts moving towards this magnetic field in this direction, the electron really has a magnetic field around it. I'm not going to draw it, but that magnetic field then gets influenced by this external magnetic field here. So I have a magnetic field that I've drawn in this region that is into the page. I'll keep it in blue for the magnetic field. So our left-hand rule would say as this electron moves towards this magnetic field, the left-hand thumb would point to the right, the fingers would point into the page, and now our palm would show that there should be a force in the downward direction acting on this thing. So this is the resulting magnetic force on that charged particle. So that's old news. That's what we studied before, and we have formulas for, and we're okay with that. Let's just extend that argument. Imagine that instead of electron just flying through space, I now take a wire. And in this wire, I have a red arrow that indicates the direction of electron flow. So if this is the directions of the electrons in the wire, you can imagine these electrons going through this wire, traveling from left to right, and at some point they enter into this magnetic field. And so you can imagine, let's get rid of that. You can imagine that if this wire is sitting still in here, the electrons inside are still moving. So the electrons are entering this side and traveling through in this direction. Well, we still have the conditions we need for a magnetic force. We have electrons moving still to the left, traveling all the way through here. They're still moving to the left, so our thumb's still pointing to the left. Our fingers are still pointing into the page. So the end result is we still end up with a force acting on each individual electron, but overall we would say there's a force, a magnetic force acting on this wire. So this idea that a current carrying wire, a wire with electrons flowing through it that's placed in a magnetic field feels a force, isn't necessarily brand new. It's something that we talked about when we talked about charges moving through magnetic fields. The only thing we need to do now is develop a formula for this. So here's the formula we talked about before. This is when the charges aren't on the wire. The force depends really on three things: the charge, the speed of the charge, and the magnetic field strength of whatever magnetic field it's in. Let's compare that to what happens when the charges are in a wire. So first of all, we're going to change our thinking a little bit. This is an I, so the magnetic force on a current carrying wire now is related to, well, similar to velocity. Now we're going to look at something called current. And current is really, in some ways, the amount of charge that moves through a wire. We'll talk a little bit about current in my next slide. But really, it's the amount of charge that moves through a wire in a certain amount of time. The force is related to the length of the wire, but the important thing here is it's the wire that's in the magnetic field in meters. So you can imagine a situation where you have a wire, I'll draw a wire right here, and maybe the magnetic field is only in a small part of the wire. So in this example, if I draw this case where we have a magnetic field out of the page here, we may have a really long wire from one end to the other, might be really long. From here to here might be, oh, I don't know, maybe it's 1 meter. But that's not what's important. We don't want to consider that 1 meter. We just want to consider what is the length of the wire that from this point here to this point here, what is the length of the wire that is actually in the magnetic field? So again, to highlight that, it would be really this part of the wire from here to here. This is the length that we worry about. So that would be our L in our equation. And finally, makes sense. We can put this current through. The more current that goes, the more force we get. The more length of wire we have in here, the more force we'll get on the wire. And finally, everything still depends on the magnetic field that you're in. So the magnetic field strength in Tesla plays a role in the overall magnetic force on the wire. So if we look back at our picture here, this wire with a certain amount of current moving from left to right, moving through a magnetic field with a certain length, and it would feel a force on it. Again, that depends on the left-hand rule will tell us which way the force is on this thing. If I rotate this wire and I take, change the orientation and I send electrons from the bottom to the top, let's just do that. So now as the electrons go from the bottom of the page to the top of the page, we'll still get a force on this because we still have a case where the electrons are in one direction towards the top and our magnetic field is into the page. So our left-hand rule would tell us that if this is the case, if that happens, we will feel a force in this direction acting on this wire. Electrons up, so thumb pointed up, fingers into the page, so fingers into the page, thumb up. Now my hand or my palm is showing me that the force on this thing will be to the right. Now, is there ever a time that we don't get a force on it, even if we have a magnetic field and even if we have current in the wire? Well, imagine if we have the wire like we have it before, moving charge electrons from the bottom of the page to the top of the page, and we put a magnetic field in this orientation. Let me draw it this way. So if I have a magnetic field, whoops, let me try that again. Let me cheat. I'll grab a little bit of, yeah, let's cheat a little bit. Imagine that I have a magnetic field that I'll draw here that goes along or parallel with this wire. So I'll just draw a few lines representing the magnetic field in this area. I'll give you an indication of the direction of this magnetic field. Let's imagine that it is down. So this represents my magnetic field direction. And now you can see, I ask you, I defy you to use your left-hand rule, your third left-hand rule. If you do, you'll end up with your thumb pointing towards the top of the screen. Your fingers now cannot point 90 degrees to that. So because the electron flow is up and down and the magnetic field is in the same orientation, we will not get a magnetic force. So in this case, we get no net force acting on the wire. And that's because we have a case where the current, in this case, or the movement of the charge, is perpendicular to the magnetic field. And when that happens, there is no force on the wire. So that'll happen if I have the wire oriented this way carrying current. It'll happen if I take the wire and move it this way and run it down in the same direction as the magnetic field. However, if I move my wire this way, now I have the conditions I need in order to have a net force on this wire. Now I do have a case where my current or my movement of charge is 90 degrees to my magnetic field. So be careful with this. As with charges moving through magnetic fields, we first of all want to decide or establish, is the wire 90 degrees to the magnetic field? Then we can start to look at what force will we have and in which direction. But if the wire ever runs parallel to the magnetic field, then you're going to get no force. And if you're thinking this through and looking ahead, you're probably imagining that if the wire runs not exactly parallel and not exactly perpendicular, then we will end up with some sort of force, just not the maximum force that we would get when it's perpendicular, not the minimum force that we get when it's exactly parallel, but something in between. All right, so let's get back to the equation. The magnetic force is equal to the current times the length of the wire times the magnetic field. So before we go too far, I do want to deal a little bit with this idea of current. And so let's have a little mini lesson within this lesson about electrical current. Electrical current really is a lot like a current in a river. It's the amount of charge moving past a point each second. If you could stand by a wire and just literally count the electrons going past a point in 1 second, you get a sense of the current in that wire. The problem is if you were to measure it in units of electrons per second, you'd have huge numbers to work with. So when we talk about current, we use the units of amperes, but really an ampere is the amount of charge in coulombs divided by the amount of time in seconds. So really an ampere is a coulomb per second. Oh, here it is right here, all spelled out for you. So 1 ampere is 1 coulomb per second. If you have a wire that has 1 amp moving through it, people will say 1 amp, you have 1 coulomb worth of electrons going past each second. Typical household circuits will have, 2, 3, 5. Your circuit breakers will trip if you have as much as 15 amps. So if you get 15 coulombs per second going through a wire, the wire heats up enough to trip your breaker, prevent any fires in your house. Just to give you a sense of the kind of magnitude or scale we're talking about when we talk about current going through wires. 15 amps is a fair amount. So I stole this question from the textbook, and let's just use that. This is an example of a, typical question in which we have a current carrying wire and a magnetic field feeling a force. So it's basic. We just look for these, just look for a key piece of information. Here we have 8.5 centimeter length of conducting wire lies perpendicular. So, I told you have to be careful about the length, but they're really implying, I think, that this is the 8.5, the distance that is actually in the magnetic field. So no real funny business going on here, although you could imagine if they gave us the whole length of the wire, you could talk about the length of the wire along here. Who cares about that, right? It's only the length of the wire that's in the magnetic field. So they're telling us that straight up. Lies perpendicular, so we're looking for that phrase, we're looking for that keyword to know, okay, we have the conditions necessary. If you were to draw the magnetic field on this picture that they supplied, it would go from the north of this magnet to the south of this other magnet. So you can see what's happening here. We have the magnetic field in one direction. We have the current traveling perpendicular to that. So perfect. That's what we want to know. We can go ahead with our calculation. And then they tell us the magnetic field is 4.2 milliteslas. So we'll make sure we convert that to teslas when we get started. They then tell us there's a negative charge flow. I'm not a huge fan. I don't think you'll see a lot of this. The textbook kind of gets a little cute with this, but really we just talk about charge flow or current, and it's 2.10 amps in the conductor. Calculate the magnitude and determine the direction, okay, going back to our hand rules, of the magnetic force on the wire. So let's take a look at the official solution to this question. So first of all, we're going to get our formula. F is equal to I times L times B. As long as we're just considering about the length of the wire in the magnetic field and it's perpendicular, we're good. We put in all the information that's relevant. We have our 2.1 amps. We got our 8.5 times 10 to the minus 2 meters. And we convert our milliteslas to Tesla. Remember, a milli is equal to 10 to the minus 3. So literally when you take milli out, you put 10 to the minus 3 back in, you put it into your calculator, we get 7.5 times 10 to the minus 4 newtons. So again, if you're keeping track of this, that's not a lot of force acting on a wire, probably not going to influence the wire a whole bunch, certainly isn't going to be something that you You'd expect to move this wire or feel any kind of pressure if you're holding onto that wire. But nonetheless, there is a force on it. And the magnitude of the force is 7.5 times 10 to the minus 4. If we want to identify the direction of the force on the wire, we'll use the left-hand rule. They're going to restate it here. It's worth reminding ourselves of it. So if we use the left-hand rule to determine the direction of the magnetic force, because the moving charges are negative, we use the left hand. Our thumb points in the direction of charge movement, or in this case, current, which is, they say, into the page. Now, just take a look at the picture again. Let me try to get a view that shows us the whole thing. They say it is into the page, but they've drawn it in a three-dimensional way. But let's go with that. It's kind of into the page and up at the same time, but we'll call it into the page. So thumb pointing into the page, fingers pointing in the direction of the magnetic field from north to south. So on this picture, towards the right. So now I have my hand pointed in such a way that my thumb is into the screen, my fingers are pointed to the right, and now my palm, just like yours if you're doing it, should be towards the top of the page. So in this case, top of page. You might be tempted to say up, but we have to be careful about that. You know, depends on which way your page is. So I'm sure nobody's, you know, if you did this on a test, they usually ask you relative to the page. So they'll refer to the top of the page or the left or right or bottom. Because our page really could be held in a lot of different ways, we can't talk about north, south, east, west, or up and down as well as we can talk about top of the page, bottom of page, left, right. All right, so I'm going to stop there. We really covered what I wanted to cover, which is this formula for the magnetic force acting on a charged particle, which is ILB. Got a sense of what the different variables represent, and some of the little subtleties, some of the things you got to be careful for. Again, that perpendicular component we got to look for. Now we got to be careful about the length of the wire in the magnetic field. And we're also getting familiar with using current in amperes and what exactly that means. Again, it's the coulombs per second. I will post another little mini lesson on converting between electrons and coulombs again, just to make sure people are comfortable with it so that we can go between the two. But for starters, if you know how to keep track of current in amperes and use the formula, and finally use the left-hand rule to figure out the direction for any forces, then we should be good to go.